again, we have some extra videos. If you go on Canvas, you can find them on page 86 in the book. Okay. Randomness of an individual outcome occurs when we take the event and we repeat it over and over and over again. Okay? So if you're to flip a coin multiple times, and you just keep flipping it and recording the results, heads, tails, whatever, that's when you get the randomness of the event. 1 or 2 flips is not random. You have to repeat it multiple times to get randomness. So what we've been doing for probability of a coin flip, we've been doing 1 flip, heads or tails, 50%. Maybe we do 2 flips and we have, you know, how much is the chance of us getting 2 heads, and we do half times a half, so we get a 4th. But we're going to calculate the probability of an event if we flip a coin 15 times or 20 times or 100 times. And that's a different formula because you don't want to have to multiply the halves and everything over and over and over again. Plus it doesn't take into account the randomness of it. So the probability of getting X successes, this is the number we want. So let's say we're flipping a coin 100 times and we want 25 heads out of that 100. X would be 25. N is the number of experiments or trials. So in that example, N would be 100. And we have a new formula for that. So the probability that X will equal A is the number of successes. We take a combination and we multiply it by our first probability to the number of successes we want times Q, which is the number of failures. So if we want heads and we want 25 heads, our probability of heads is 1/2 and A would be 25. Our probability of tails, Q, tails is the failure. If we're looking for heads, tails is a failure. Heads is a success, tails is a failure. Does that make sense? That would also be 1/2, but it would be to the number of trials minus our successes. So if we want 25 successes, then it would be 75 over here. Okay? So, and then just a reminder, if you don't have the calculator that'll do this for you, there's the formula for combination. Okay. So let's look at that example I was just giving. Let's say I'm going to flip 100 times, and I want 25 heads. Okay. In that scenario, A is 25, N is 100, P is the probability of heads, which is 1/2, and Q is the probability of tails, which is also 1/2. That's how I'd break that down. For example, we have the probability of scoring above a 75 is 40%. Okay, so if above a 75 is a success, that's P. We want to know what is the probability of scoring below a 75. That would be Q. And in this case, not a failure that if you get below 75 you failed the test, just a failure in that we were wanting above 75, not below. So maybe we should call it not successful instead of failure. Okay. So if our total probability is going to be 100%, above 75%, the probability is 40%, that means our probability of below 75% is 100 minus 40, which is 60%. In our equation with like multiple experiments, this is going to be P, this is going to be Q. So if we were looking back at this formula over here, that's P and Q. So we'd have put a 0.4 in for P and a 0.6 for Q. Does that make sense? Okay. A fair die is going to be rolled 10 times. And X is going to be the number of rolls in which we see a 2. So A, what is the probability of seeing a 2 in any one of these rolls? Well, there's 6 sides. One of them's a 2. So the probability of a 2 is going to be 1 out of 6. So far, okay? Now for B, we're going to have to use the formula. We want to know what is the probability of us seeing a 2 exactly one time in 10 rolls. Okay, so for this, we want exactly once. That's how many successes we want, so that's A. A equals 1. We're doing 10 rolls, so that's N. Okay, our probability, our P, is our success. That's A, the answer for A. So P is 1/6. Q then is going to be 1 minus 1/6. So that's going to be 5/6. To make these easier to work with, I'm going to convert them to decimals. So 5 divided by 6 is 0.83 repeating. Okay. So we're going to plug that into our formula, which again NCR. Hold on. I need to remember. I want to write it down 100% properly. NCA. So our probability that X will be 1, so we'll see 1, 2 in the whole time we're rolling die. We have N is 10, A is 1, times 0.167 to the 1, times 0.833 to the 10 minus 1. So that's to the 9th. Okay, 10C1 is 10. 0.167 to the first is just 0.167, and then 0.833 to the 9th is 0.193. And then we multiply those three things together, and I get 0.322, which is a 32% chance that when I'm rolling 10 times, I'm going to see 1, 2. Which means that there's a 68% chance that I will see more than 1, 2. All right, let's look at this. We have 15 times, so that's N equals 15. X is the number of rolls in which we see a 2 again. All right, here we go. We want to do the probability of seeing a 2 in any one of those rolls. Well, we've done that. We've got 1/6. And then the probability of seeing a 2 in exactly 2 times. We've just done exactly 1 time. Now we're going to do exactly 2 times. So in this case, A is going to equal 2. So we're looking for twice. So A is 2. N is 15. The P and Q haven't changed because we're talking about the probability of rolling a 2. So P is 0.167 and Q is 0.833. Okay, so our probability that X is 2 now, so we're trying to find a 2, we have 15 C2 with 0.167 squared, because we've got 2. And then we have 0.833 to the 15 minus 2. Okay. When we calculate 15C2, I'm going to do that in the calculator. Okay, so I'm calculating that. That's 105. 0.167 squared is 0.0279. 0.833 to the 13th is 0.0930. And when we multiply that out, I get 0.272, which is 27.2%. So my probability of getting exactly 2 2s out of 15 rolls is 27%. These are binomial experiments. Binomial experiments, can't speak today, have a fixed number of trials. 10, 100, 50. You have a set number of trials that you're going to conduct. And each trial is independent of the other. That means my first roll will not affect my second roll. Whatever number I get on the first roll is, like if I get a 2 on this roll, it's not going to make me not get a 2 on the next roll. They're all independent, right? And there's only 2 outcomes. Okay? The outcomes are success or failure. If I'm trying to roll a 2, I'll either roll a 2 or I won't roll a 2. There's no other options. I'm not going to roll kind of a 2. It's a 2 or it's not, right? Makes sense? This is why there's binomial, bi meaning two possible outcomes, success or failure. You know ahead of time the number of experiments. Okay. And each happens separately. Okay, so I'm not going to, if I want to roll, for example, in the die, for it to be a true binomial experiment, if I want to roll a die 15 times, I don't take 15 die and roll them all at once. I roll one die 15 times. Okay. Now, would your results be different? Maybe. Every time you roll a die 15 times, your results are going to be different, though. So, who's to say? But in an ideal definition, every event, every experiment is happening separately. You're not conducting more than one at the same time. Okay, does that make sense? And again, only 2 outcomes, success or failure. So it's a 2 or it's not a 2. Okay. Oh. All right, so let's look at this. We have a pair of dice. So now we have 2. They're being rolled 10 times. And X is the number of rolls in which we see at least one number 2. Okay, so what is the probability of seeing at least 1, 2 in any of the rolls? So I have to make one of my lovely tables. But instead of doing a sum table this time, because I'm not asking what the sum is, I'm asking how many times will I see at least 1, 2. So here I would have 2 1s. Here I'd have a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. Here would be a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6. And then if I go down the column of 2s, I'm not going to have any 2s here, and I'm not going to have any 2s over there. The only reason I would need to fill that out is if I didn't remember how many possible combinations there were when I'm rolling 2 dice. Do you guys remember? 36. Okay, when I'm talking about 2 dice, and I'm talking about the sum or combination, there's going to be 36 total. Okay. Out of those 36, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times that I see at least 1, 2. This one only gets counted once. Does that make sense? So there's 11 times there's at least 1, 2. Let me write that out so it doesn't look like I wrote 12. Okay, so my probability of 1, 2 is 11 out of 36, which is a 0.306. Okay. Now for B, what is my probability that exactly half of the rolls we see a 2? So in this case, A is going to equal 5. N is 10. P is 0.306, which makes Q 1 minus 0.306. Which is 0.694. Okay, and then again my formula. Okay. So I have 10 C5 times 0.306 to the 5th times 0.694 to the 10 minus 5. 10 C5 is 252. 0.306 to the 5th is 0.00268. And 0.694 to the 5th is 0.161. And when I multiply those together, I get 10.9%. Before we had a binomial distribution, now we're going to have a multinomial distribution. We've got a bag of marbles, and in that bag there's 5 red, 4 white, and 3 blue, and we're going to calculate the probability that 6 times we pull out a marble, put it back. How many times we will pick 3 red, 1 white, and 2 blue? So it's not binomial because there are more than 2 possible outcomes. Your outcomes are red, white, or blue. Hey, 4th of July, woohoo. Okay, so a multinomial distribution is one in which there are 3 or more outcomes. It's not just success and failure. It's, did I grab a purple one, or a blue one, or a green one, or a yellow one? Something like that. So we have a formula for that as well. We have our total number of experiments to the factorial times our individual results, etc., times our probabilities of the first to that individual result, probability of the second to that individual result, probability of the third, etc. Okay? N is the number of trials. N with a little number on it is the number you want. So for example, in this case, if I have 3 red marbles, N sub 1 would be 3. N sub 2 would be 1. And N sub 3 would be 2. And we can have 3 or more, so there could be like N up to N sub whatever and P subs whatever. Okay. We'll actually work this problem out just in a second. Same problem, same formula, so let me write it down really quickly. a 1, not an I. And I'm only going to 3 because we have 3. Okay, n is our number of trials. We are going to do 6 trials. So n is 6. Probability of a red marble. Well, first I need to figure out what are my total number of marbles. I have 5 red, 4 white, and 3 blue. So I have 12 marbles total. My probability of a red marble is 5 out of 12. So that's 0.416. My probability of a white marble is 4 out of 12, which is 1/3. So that's 0.3 repeating. And my probability of a blue marble is 3 out of 12, which is 1/4, so 0.25. So far okay? Now my n subs, I want 3 red marbles. That's n1 because my probability of my red, white, and blue, I'm going to do red, white, and blue here too. So n1 is 3, n2 is 1, and n3 is 2. Now I just got to plug all of these numbers in. Okay, so n is 6, n1 is 3, n2 is 1, and 3 is 2. And then I need to multiply that times my probability. So red to the power of 3 because I want 3 reds. And then white to the power of 1 because I want 1 white. And then blue to the power of 2 because I want 2 blues. Okay, 6 factorial is 720. Divided by 6 times 1 times 2. And then 0.416 to the third is 0.7199. And 0.3 to the 1 is, hey, 0.3. And 0.25 squared is 0.0625. And when I divide this and then multiply it by those, I get 8.9%. Well, actually 8.99, but it's good enough. Okay, let's try another one. We are randomly drawing cards from an ordinary deck of cards. Ordinary meaning there are 52 cards. Okay, every time I pick one, I put it back in the deck because I'm just like playing a game and I'm bored. Okay, I'm going to do this 5 times. What is the probability that I draw 1 heart, 1 spade, 1 club, and 2 diamonds? N is 5. This is n sub 1, n sub 2, n sub 3, n sub 4. My probability. Probability of a heart is the same as the probability of a spade, is the same as the probability of a club, and is the same as the probability of a diamond. Do we all agree on that? Because there's an equal number of each, which is 13 out of 52, which is 1/4 or 0.25. Okay, so my probabilities, probability 1, probability 2, and 3, and 4 are all the same. So far, okay? So, my probability of drawing a heart, a spade, a club, and 2 diamonds is 5 factorial divided by 1 factorial times 1 factorial times 1 factorial times 2 factorial. times 0.25 to the 1 times 0.25 to the 1 times 0.25 to the 1 times 0.25 to the 2. These numbers down here should match your exponents up here, always. All right. Yes, you can. This is exponents with common bases, so this part right here would be the same thing as 0.25 to the 5th. So you just want to make sure you got that correct if you were going to take that shortcut. I'm not going to take it this time, though. 5 factorial is 5, 2 factorial is 2, 1 factorials are 1, and if I multiply a bunch of 1s and 2s, I get a 2. Times 0.25 times 0.25 times 0.25 times 0.0625. And when I multiply that all together, I have a 5.86% chance of just randomly drawing cards out of a deck and pulling out 1 heart, 1 spade, 1 club, and 2 diamonds. Yes? Yeah, you could put 6%. When we're spinning a spinner, you guys know like the spinners for like Twister or, yeah, okay. We have an equal chance of landing on orange, green, yellow, red, or black. Okay, so there's 1, 2, 3, 4, or 5. So the probability of any color is 1 out of 5, which is a 0.2. Okay, because there's an equal chance. So let's say we spin the spinner 12 times. What is the probability of landing on orange twice, green 3 times, yellow twice, red 3 times, and black 2 times? Okay, so we're doing 12. And I have orange, green, yellow, red, black. And my probability for each of those is 0.2. Okay, now this is something that I didn't really do in the last one, but see how I have all 0.2s, everything's the same? When this happens, to make my math easier, I have 2, 5, 7, 10, 12. Add up my exponents. I have 0.2 to the 12. Do you guys remember that? Okay. From algebra? So 12 factorial is a very small number. 479,001,600. Very small number. And then when I have my denominator, I have 2 times 6 times 2 times 6 times 2. So far, okay? Okay, and then I need to do 2 to the 12th, or 0.2 to the 12th, sorry, 0.2, whoops, to the 12th. Hold on, let me make sure I get the right number of zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros. And when I multiply and divide and do all my math, I'm going to get yes, it is a lot of zeros. So it ends up being, though, only 2 zeros. So I have a 0.68% chance of landing on orange twice, green 3 times, yellow twice, red 3 times, and black twice. Very unlikely to happen. In Australia, 30% of the population has a blood type of O. When you get a statement like that, that means the probability of an O is 0.3. Probability, sorry, it's O positive. Probability of an A positive is 0.33. Probability of a B positive is 0.12. Probability of an O negative is 0.08. Probability of an A negative is 0.03. And the probability of a B negative is 0.01. So the percentage is the probability. Okay, so we're going to pick out 15 Australians, and we're going to figure out the probability that 3 of them have an O positive, 2 have an A positive, 3 have B positive, 2 have AB positive, 1 is O negative, 2 are A negative, and 1 is B negative, and 1 is AB negative. I forgot to put that one. Oh, that's a 3. I messed up my probabilities. Hold on. 30% is O positive, 33% is A positive, 12% is B positive. Aha. 6% is AB positive. 7% is O negative. 3%, 8% is A negative. 3% is B negative, and 1% is AB negative. All right, so let's figure out this probability. Okay, I've got 3, 2, 3, 2, 1, 2, 1, 1. And I've got O positive first, so that's 0.03 to the third. And then A positive, which is 0.33 squared. B positive is 0.12 to the third. AB positive is 0.06 squared. O negative is 0.07. 1. A negative was 0.08. So that's 2. I'm running out of space. So B negative was 0.03 and AB negative was 0.01. So far okay? Did I lose you? Are you sure? Because I'll go back over it. Okay. Okay, 15 factorial is this big old number. And then my denominator, I'm going to take the 1's out because 1 times anything is just 1. So I get 6 times 2 times 6 times 2 times 2. And then my decimals taken to their various exponents. Okay, and when I multiply these together and divide this, I get another really short number. Times another really short decimal. And when I multiply those together, I get so I have a 0.0011% chance of randomly picking 15 people and having these blood types. So I'm going to go out on a limb and say it's not going to happen. Because that's just so close to 0, I am feeling very confident that it's not going to happen.